theory or effective field theories, and then dive into a little bit what the low energy excitations look like in these systems that we're interested in, specifically deformed odd nuclei. The symmetries that we're assuming in the theory, the Hamiltonian and the spectrum that we come up with for the theory, as well as some applications to particular cases. Again, some background on what we mean when we talk about effective field theories. It's a tool that's pretty broadly applicable throughout broad ranges of physics, from black holes and cosmology, all the way down to nuclear physics, to even being used to try to extend the standard model. And one of the reasons that it's so broadly applicable is the way that we exploit this separation of scales, which occurs in many systems, whether we're talking about the top here of something like chiral effective field theory, connecting quantum chromodynamics to the physics of hadrons and mesons, physics of nucleon, to effective theories such as this one that connect us from the physics of nucleons to more collective degrees of freedom. This separation of scales is something that is pervasive throughout this. So one of the other helpful hallmarks of effective field theories, or effective theories in general, is describing the system in terms of relevant degrees of freedom. You very rarely see nuclear structure described in terms of QCD, well, gluons, right? And with the sort of higher energy degrees of freedom, we essentially integrate those out, which can be, is sometimes done explicitly, or very often is done sort of implicitly, fitting low energy constants to data, which we will come to in a moment here. And specifically in quantum systems, such as nuclei, we are expressing operators as sort of systematically improvable series. Again, one of the benefits of effective field theories such as this is the systematic nature. One of the traits of theories that break things down into series such as this is they will always have a breakdown scale, sort of a radius of convergence, if you think in terms of function series. And this is, in some ways, a hindrance, right? You can't extend this theory to everything, but it also gives us a lot of power in terms of describing uncertainties. So very often we'll say that this is really a feature of the theory, not a bug. And another hallmark in terms of these theories is once you've laid out the symmetries of the theory and chosen your specific degrees of freedom, all operators that are permitted by those symmetries have to be considered within the theory. It gives, that's what gives us our power to, describe whatever excitations we have within these systems. And again, with the the separation of scales that we have. It also allows us to expand these operators according to contributions according to their relevance. So beginning with sort of a crude leading order description, and sort of applying higher order corrections on top of that, which in general are suppressed by some ratio of the energy scale, or very often, it could be a ratio of length scales, momentum scales, but in some higher order terms are suppressed by higher powers of that sort of ratio of scales. Another hallmark of the breakdown scale is the series expansion will only improve, or the description for the theory will only improve up to that breakdown scale. This is essentially, so above that breakdown scale, in general, your leading order theory may actually provide better predictions than, next to leading order or next to leading order, which we will see later on. But yes, and here we have a depiction of some relevant effective theory or effective field theory in terms of nuclear physics. We have a picture of a halo nucleus here. This is, I guess, depending on your preference for red neutrons or blue neutrons, is a nucleus with a 1 neutron halo or 1 proton halo. And sort of the, we can see here kind of that separation of scales depicted. We make this assumption that the energy scale associated with the halo neutron or proton is well separated from the higher energy excitation sort of within the core of that halo, which is a similar assumption to what we'll make in our theory going forward. Talking about low energy excitations in these nuclear systems, this, we have excitations at varying scales, going from pairwise excitations in nuclei to sort of nucleonic currents and densities, current all the way down to collective excitations such as vibrations and rotations, and rotations wind up being the lowest of these. So we really are describing sort of the lowest energy, lowest energies in the spectrum here. So the symmetries that we are assuming in the theory, we take on all of the symmetries of QCD to begin with. So we assume invariance under, as well as sort of isotropic space. So invariance under SO3 rotations. But because we're talking about deformed nuclei here, the states themselves will sort of break down that SO3 rotation symmetry down to SO2 axial symmetry. And we see here a little bit of a toy model of the leading order description of the theory here, where we have we've basically integrated out it's on the nucleons within sort of the what we might call the core, which is not necessarily a core in the same sense of a halo EFT. These are not necessarily all loosely bound nuclei. But we, in a sort of a more crude way, assume that sort of the associated even nucleus forms a relatively inexcitable core, which sort of informs how we choose our breakdown scale and things on top of that. So we have that, and then coupled to the two free nucleons here, or the two unpaired nucleons. And specifically, they are coupled by their total angular momentum. The individual states in any spin isospin couplings, we really don't consider for reasons that we'll come to a little bit later. But really, we are just sort of coupling the orientation of this rotor, which we consider to be a rigid rotor at leading order, coupling that to the total angular momentum state of these nucleons here. So to talk a little bit more about the relevant scales here, the lowest or the low energy scale and the breakdown scale of the theory are we sort of consider to be set by the even core nucleus. So we see depicted here. There we go. The breakdown scale, which we essentially consider to be the first the lowest non-rotational state within the spectrum of the core. So in this particular instance, we look at the odd nucleus, rhenium 182, and the associated even core of tungsten 180. So we again see that we have a reasonable separation of scales. The ratio of those energies gives us about a factor of 10 to work with, which is, in some sense, something that you can do some perturbations with. So that sets sort of our low energy scale and our breakdown scale. There is another scale to sort of consider here in terms of breakdown of the theory, which is the scale for single particle excitations within the nucleus. Those are, they tend to be lower energy in odd nuclei, such as this, because we have unpaired nucleons. In the ideal case, we would assume that this low energy scale for rotational states is much smaller than both the single particle excitation scale and the breakdown scale. We'll see that is very often not the case for these nuclei. So here we have the excitations for rhenium 182. And we see here that the sort of spacing between bands is really not much higher than that in the low energy scale here. In this particular case, it's not as bad as many, but it is enough that sort of unwanted couplings start to appear, which can complicate our description a little bit. It seems like a problem. We'll find that it's seemingly not as much of a problem as it seems. As far as describing these things, in order to get a spectrum to really work with, we need to construct a Lagrangian. So looking at the relevant degrees of freedom that we've got here, We have the sort of orientation of that even core. That again, at leading order, we assume is a rigid rotor. That together with sort of its associated velocity, as well as that total angular momentum of the unpaired nucleons here. Now, we do assume that this sort of the core moves slowly enough that we can employ an adiabatic approximation. So we assume this K here to be relatively constant, sort of processing with the nucleus as it undergoes these rotational excitations. With the sort of symmetries here, the sort of sign associated with these transformations here, we can build, terms of a variety of shapes, for at the leading order description of the rotor itself. We see terms of, v squared, or terms proportional to v squared. We also get a sort of familiar Coriolis coupling with this term of the form, v dot er cross k. We also include a term proportional to that, that with an undetermined strength. There is one of fixed strength that appears as well, or a contribution that appears of fixed strength. But because of the other contribution appearing that has an undetermined strength, we absorb it all into one low energy constant. Essentially mashing these terms together and categorizing them according to their the size of the contribution that they make to the Lagrangian or Hamiltonian. We get something that looks like this. We build off the theory to next to leading order. And again, get something that looks like this. So these, the low energy constants associated with these are essentially assumed to be smaller than this, smaller than the low energy constants associated with the leading order contributions here. Notably, we do get, we can describe this interaction here and summarize it as a gauge coupling, which is interesting that we get this sort of thing that looks and feels a little bit like a magnetic potential, magnetic vector potential that creeps in, but is most certainly not. So that gives us some idea of the scale of these contributions. And after performing a Legendre transformation and introducing the appropriate angular momentum associated to the Lagrangian up there, we get a Hamiltonian that looks something like this, quantized in terms of the total angular momentum and these contribution or these sort of familiarly defined ladder operators for angular momentum. So looking at the spectrum of this, the leading order spectrum, nothing terribly new. This is sort of what we expect for rigid rotors in quantum mechanics. And this additional operator here, Coriolis-like coupling, is capable of connecting these states with angular momentum projection k and k plus 1. or -1, I suppose, depending on how you want to define those. And the contributions that they make to the energy will be essentially the eigenvalues of this matrix, where this G tilde here takes this form. And notably, this coupling does depend on the total angular momentum here. So those couplings get stronger as we sort of go up in the rotational band. So at next to leading order, we have a very similar thing. We get sort of this contribution of deformation, further deformation of the rotor core that are again kind of suppressed by this factor of C1 prime or C naught. And again, we see some new couplings to the between rotational states, and because we have this operator squared, we can see couplings between states that differ by 2 units of angular momentum. So exactly what that means is in terms of odd mass nuclei, which, wow, that's lower resolution than I thought. But this is a rotational spectrum for plutonium 239, which has a rotational ground state band starting with k pi equals 1/2 plus. And if you consider these types of couplings that can occur due to that Coriolis operator between k and k plus 1, because we have this this sort of degeneracy that occurs between angular momentum plus 1/2 and minus 1/2. Plus 1/2 and minus 1/2 do in fact differ by 1 unit. So this coupling can connect that rotational state to itself. And this manifests itself as a staggering within the rotational band. Again, the numbers are a little bit harder to see than I anticipated, but we can definitely at least see the very staggered spacing as we go up in the rotational band here. And even in some nuclei, interestingly enough, you can actually see an inversion that happens here where this 1/2 state is actually moved above the 3/2 state that sort of would come above it in the rotational band, which is always interesting. But this our effective theory here is really not to describe odd mass nuclei, but really odd nuclei. So coming back to the example that we looked at a little bit earlier of rhenium 182, we've formed a description here of this third rotational band here. You'll notice the X's here in the spectrum from NNDC. Essentially, that's just because we haven't observed or haven't sufficiently observed decays between these states and states that have been properly placed within the rotational spectrum. So if I back up here for a moment, within this spectrum here, you'll notice these little blue arrows that indicate decays between these states. None of these arrows go down to any of these states in band 3 here, and none of these states in band 3 have arrows that go sort of outside of this as well. So that is essentially why we have those unknown energies appearing in there. But what we're really describing are differences in energy anyway. So we have that, and the lack of interaction between those bands is almost a comfort here anyway, because the it may indicate that these bands just have vastly different structure. So we can consider this as a sort of an isolated rotational band. So we have here our leading order description, starting at the 2+ state at the bottom. And we can see here our breakdown scale. And here we don't have any couplings to speak of. Again, because we can most likely consider this as an isolated rotational band. So looking at the sort of scale of the low energy constants that enter, we have the values that we get from fitting, and then also the estimates that we got from the Thomson 180 core here. So we see that these are not spot on, but for as crude of a theory as we have, assuming that our degrees of freedom are essentially a rigid rotor core, coupled to the total angular momentum of the unpaired nucleons, with no spin isospin couplings at all. It's, if you squint at it hard enough, maybe, these are of the same order of magnitude. In looking at the next to leading order description here, we see that the C0 that we fit is relatively close to what we got for leading order, and the associated constant for sort of deformations of the core beyond that is seemingly smaller than one would expect, and we will see that a couple more times here. But some good, maybe better news comes when we look at this log error plot here. We see that when we look at sort of fitting a best fit line to the absolute error versus the energy here, which corresponds to fitting a power law to the raw data. This crossover point here is sort of the real breakdown scale, where we actually do start to see the next to leading order description performing worse than the leading order description. And if we compare that, this breakdown scale of about 700 keV to our estimate from the even core, again, we see that it is of the same order of magnitude. So for sort of back of the envelope calculations, that is not nothing. So if we'd calculated this to to higher orders, say next to leading order, or N2LO, we would obviously lose a couple of data points back here to the coefficient fitting. but we would expect a steeper line here. Ideally, our power counting should have these as powers. This should be in an ideal world, this should be e to the second and e to the third. See, we're not quite on that, which may suggest that we've missed something in our power counting argument. But again, not the worst that you could expect. So looking at another example here, we looked earlier at sort of a self-coupling that can occur due to the Coriolis-like operator, the k plus I minus plus k minus I plus. We also have at next to leading order that operator squared appearing in the Hamiltonian. So in the case of k equals 1 bands, that can also induce a self-coupling. Because it's a next to leading order effect, obviously we see that the staggering is not quite as marked as it was with the k equals 1/2 states. It still gives us, it's definitely visible as we go higher within the rotational band. Let's take a look at what we get as far as fitting here. Again, we fit the spectrum at leading order. This at leading order, again, appears the same as the rigid rotor, the rigid rotor spectrum. So we don't see any kind of staggering effect over here. But when we move into the leading order description, we do see, we see that it matches that staggering fairly well up beyond or up to the breakdown scale here. And again, as we'd stated before, we do see that our leading order estimate above the breakdown scale is, really a better approximation than the next to leading order description, which again is sort of a property of that quote unquote radius of convergence or breakdown scale of the theory. So again, looking at the leading order fit here, we have not a bad match between these. Again, this is estimated from the sort of even core nucleus. I believe 178 hafnium. If one were to look up that spectrum, and looking at the next leading order description here, we see a little bit of a jump. These should actually be C zeros to the -1, not just C zeros with the dimensions of energy that we have here. And then looking at our next to leading order contributions, again, estimated those should be on this scale of about half a keV, which the constant associated with the self-coupling does appear to be on that same order of magnitude. This is less so for the sort of I to the 4th correction, or the deformations within the even core. So looking at our error plot here, again, we see that that breakdown scale appearing here at about 1800 keV or so, which gives us a reasonable chunk of predictive power in these in these rotational states. Thank you. So that gives us something reasonable here. Something interesting to note, we see here in our leading order description, our absolute error is scaling as the energy to the first power, which really suggests that we are missing something in the leading order description for these k=1 rotational bands in odd nuclei. That may suggest that this coupling here should actually be considered a leading order coupling, even though it's produced by or induced by that Coriolis operator squared. Yes. A couple of conclusions that we can try to make here. In general, deformed odd nuclei are reasonably well described by this sort of quasi-particle rotor model at leading order. Again, that quasi-particle rotor model being the way that we couple the total angular momentum of the free or unpaired proton and neutron to the even rotor core. The single particle excitations described by that scale or the average spacing between rotational bands in the spectrum of the odd nucleus. That turns out not to greatly influence the breakdown of our theory, because when we look at these, comparing this, sort of the low energy scale here to this separation, we really don't have a massive separation. And I believe even in tantalum 180 that we have rotational bands that may be actually have lower band heads than this. Really that lack of separation between the single particle excitations does not necessarily seem to throw a wrench into our theory as one might expect. I suppose the biggest takeaway that maybe was less evident within the slides is when it comes to finding fitting an effective theory to data like this for odd nuclei, we really just don't have a lot of data. These spectra are sort of very wide. There are a lot of rotational bands that are spaced very close together, and a lot of potential couplings that can occur, and just not a lot of rotational states within those bands. So the handful of examples that we saw here are really sort of needles in the haystack. Have enough data. It does appear that especially our leading order description of these nuclei as rigid rotors coupled to those nucleons via that gauge potential does work fairly well. To thank a couple of folks here, I want to say thank you to my advisor, Thomas Pappenbrock. Thank you to Andrea Delgado, the director of the internship program that I started this research in 2 years ago. Thank you to James Singh for the invitation to come here. Thank you to all of the FRIB faculty, staff, students for being all around wonderful. And most of all, thank you to everybody in the room and in Zoom land for listening. I want to open up the floor to questions.
Right. Any questions? Maybe I can start quickly. So I wasn't sure why this can't be applied for like two neutron or two proton. Like even if they don't have to be paired, right?
Correct. Right. So they would not have to be paired for this to work, or they don't have to necessarily be a proton and a neutron for this to work.
And then maybe you could find more data in a way in that case.
That is true. Yeah, I guess that is something to look into. I think our goal with this, I guess, was to work with a sort of smaller amount of input from from these spectra and less input from things like a Nielsen model to determine whether these are in fact paired protons or unpaired. But that would certainly be something interesting to look at and might actually be something that I look at in the next few days here.
Okay. Okay. Any other questions? Maybe if you can go back to that slide which had those terms that you had in your effective field theory.
Yes.
Yeah. This one.
This.
Yeah. So you have etc. I was maybe I missed it. Do you have anything over the square term? Like, do you have higher than square terms?
Yes. So because these terms are permitted by the symmetries, you can also have any higher power of these terms.
Okay.
So squares, cubes, any of those of these, and essentially any of these operators squared works. So for instance, K squared terms would be permitted in the Lagrangian that we have here. Any of those terms that are just K squared, we would really lump in with this sort of L psi, or sorry, over here.
I see.
Because those are, I guess what we might say are solely dependent on the unpaired proton and neutron, rather than rotations of the associated with that.
I see. Okay, interesting. Okay, any other questions? Ceiling.
So have you considered electromagnetic transitions in this theory?
We could, we have not, but hypothetically, that's something that that we could do. Looking at the essentially building that operator up out of the same sort of symmetry appropriate terms, with the appropriate low energy constants.
Mark.
Sure. This is probably something you cannot answer on the fly, so don't feel obligated to just on this very slide, since it reminded me. My general understanding is that the idea with axial symmetry is that the SO2 quantum number, projection of angular momentum along the intrinsic axis, is a good quantum number, but that you'd be in a superposition of many, that it's not an actual K angular momentum vector. Do you have any ideas if you could generalize the theory to allow for just good K projection, but not actually assuming a classical vector K there?
So the vector K there really only survives into the Lagrangian here. Once we quantize, we we really don't have a good a good K vector. Like it really that angular momentum is no longer
Okay,
conserved.
thank you.
You think?
I have two questions. The first is about proton-neutron coupling. So you have this proton-neutron pair, which is coupled to the core. But of course, there is a residual proton-neutron interaction
Yes.
between those valence particles. And we know a lot experimentally, for instance, about this coupling. It depends also on angular momentum. So what do you assume for the Hamiltonian of the pair? So this is first question. And the second is that the core is never rigid in atomic nuclei, right? So core consists of protons and neutrons. And in particular, as you rotate the nucleus, there will be pair breaking effects in the core, which manifest themselves through phenomena such as backbending, angular momentum, alignment, etc. So how do you account for such effects?
So for to address the first part of your first question about couplings between the unpaired proton and unpaired neutron, we could have couplings between those. We essentially assume that those aren't there because we would in general have to sort of assume that coupling has an unknown strength, right, in this effective theory framework. And in our sort of already sparse data set, we made the decision to really just to not consider that and lose more of our predictive power to that additional constant. We made that assumption. That may be one of the as far as looking at these power laws not coming out exactly as we expect. That's could very well be one of the reasons that that doesn't come out that way. So it could be something that we go back and look at how looking for. We could go back and look at that that interaction to see if we can get a better description for that see if we get an appropriate change in that sort of chi-square as we add in that extra degree of freedom. And coming back to your second question about handling the deformations that occur within the core. So we essentially do that. We handle that by the core is we assume that the core is rigid at leading order, not in general beyond that. So we like those stretching effects, for instance. The effects of those would be summarized in terms like at least classically would be summarized in terms like this v to the fourth term here, which then goes into I to the fourth term down here. But we're essentially I guess looking at it almost like a black box, right? As we don't know precisely how this stretching occurs, but we know that the stretching is not leading order strong. So we say that there's no stretching at leading order. Whatever the stretching is, you know, because we know it's not happening at leading order, you know, we should be able to summarize at least the first contribution to that those stretching effects in this this term here. You know, assuming that we have a good power counting, we should be able to summarize this sort of at least before we start hitting next to leading order effects. I'm not 100% sure if I got to the heart of your question.
I was really thinking about the pair breaking effects, which have little to do with deformation degrees of freedom. So pairing field is another collective field in the atomic nucleus,
Right.
which would be impacted by rotation, right? So you already concentrate on deformation in this work. What I want to say is that coupling to pairing field might also introduce additional terms in your Lagrangian.
Right. And if I remember correctly, I know that there is there is work in there's work that's been done on a couple of different classes of nuclei and sort of building effective theories for pairing effects. I think that those are, most of that work is in you know, approximately spherical nuclei. So would not overlap very strongly with this, but I guess that is I think that would be I guess feels like another avenue of study, sort of separate to this one, to sort of look at the intersection of those two, looking at those pair breaking effects within in deformed nuclei such as this.
And that's also a EFT, so that
Yes.
works.
Yeah.
Anything else? Other questions? Any questions from the Zoom? Any? Okay, then let's thank Jordan again.
Will you be your